Hello Math 112 fans. Trying a different approach. I just went through and did this exam very quickly, this spring 2023 exam 1. Now I'm going to do a graphical explanation of each problem, and I hope this just gives you a better understanding. I think it's kind of interesting in itself. So let's play this game. I'm just going to go back through, look at the solutions we just made, and then I'm going to show you visuals. Okay, so the first problem we did was this derivative. This is a messy function. Here it is. I typed it in here. We computed the derivative. The derivative tells us the slope everywhere. This is a pretty interesting graph. It has asymptotes. There's all sorts of things going on. But now we can see this. We can see, it's going to go too fast, but we can see all those tangent slopes. There they are. We know how to find them. That's what the derivative represents. For example, you could figure out when the slope is 0. So at negative 0.5, the slope is about 0. Now where did we go? We went to 1. So if you go to 1 and figure out the slope, it's extremely steep. The slope is 159, meaning if you go over 1, you go up 159. That's what we're doing. The power of calculus is it doesn't matter how complicated this thing is, we can study the slope. No problem. Next one. Okay, so then we have this foundational question. We were starting with the function 3x to the 4th, which is just this parabola. 3x squared minus 4, sorry. And then we said, well, if we have a point and we want to know what the slope is, what we're going to do is we're going to grab another point nearby. So there's kind of, this is the calculus idea where everything starts. And we say we're going to find that slope. We know how to find the slope because you can just do change in y divided by change in x. The clever idea is to use h, but the reason we do that is because we want to make h smaller and smaller and smaller and smaller. And the smaller it gets, the closer it gets to being a tangent line. Now you can't have a slope right at a point, it just vanishes. So we have to do some simplifying and try to see what's happening as we approach. Okay? And it turns out that's possible. Right? So that's what we did. We said if you plug in x, then you plug in x plus h and simplify, the slope is 6x plus 3h. Now we can't plug in h equals 0 initially, but we can see that the final simplified answer gets closer and closer to 6x. And then we can use that to find the actual slope. That's where all of this game started. Okay, then what added piece? What if I want the tangent line at 2? Well, let's go to 2. Let's find that particular line. In order to find a line, you need a slope and a point. But you have a point. At 2, the height is 8. And the slope is 12. And so we're just giving the equation of the line that has height 2 and slope 12. That's all that is. But there's a physical picture. All right, let's keep going. So then we're given the derivative graph. And this graph's going to have a bunch of stuff in it. This is more complicated, more stuff going on. I'm going to get rid of all these other things. So in this case, they only told you this derivative graph. This is this A. And you were having to make various conclusions about it. I don't know why that's showing that way. Oh, the labels are still showing. But this represents the slope of something we can't see. And when you're thinking in terms of slope, we immediately think, when is it 0? When is it positive? When is it negative? So let's track along this and see it's negative everywhere over here, and then it's 0, and then it's positive, and then it's 0, and then it's negative. That's how you read a derivative graph. But negative here means if you could see the original graph, it's going downhill. So what I decided I would do is show you the original graph right above it. Usually we don't put them on the same axes. And let's draw a little line connecting them in case you can't see this. So there you go. The slope is negative there. Do you see that? It's downhill. In the derivative, it's negative. In the function, it means downhill. Here, I'll draw the tangent line for you. There it is. It's downhill, 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 till right there. And that's a place where you have a little bump, a little low point. And then it's uphill, 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 and then 0 again. And then downhill, downhill the rest of the time. That's what's going on. So there we go. Let's go here. Let's make it animate a little bit. So there we go. Downhill, downhill, downhill. 0, uphill, downhill again. So you always have to pay attention to which graph you're looking at. Okay, now to the question. The question says, give the longest interval when balloon A is rising. Balloon A is only rising in this little segment here when it was going uphill. Let's zoom in. Balloon A was rising right here. Let's get rid of this line. So it was rising from here to there. Now in the graph we were given, what would those points be? They would be the points where the slope is 0. So from here to here. So you had to realize this question was, they gave me the slope graph. It says it a few different ways in bold. And the question is asking me when I stop rising and start rising. So I need to find when the derivative is 0. You have to realize this is the derivative of height. That was the challenge. Give the time when it's rising fastest. Now rising fastest is going to be somewhere in the middle here when it was going up the fastest. And it's going to be wherever that was biggest. So this is more a problem just keeping you honest. You know how to find the high point of the graph you're given. Okay, so then it gives me another balloon. Let's talk about that one. Here's balloon B. Let's get rid of these labels, too many things. There's the height of balloon B. You might try to picture what the derivative would look like. If you took the derivative, it should be uphill and then downhill. Let's take a look. There's the derivative. Let's draw that same sort of line. And let's see what's happening. So the derivative is positive when this is uphill. Okay, and then it's 0 when it gets to the top, 0 when it's at the top, and then when it's downhill, negative, downhill. Now, in a given problem, you typically can only see one or the other, and so you have to understand the translations. You have to know what you're looking at. If that's a derivative graph, then that corresponds to when the slope is 0, slope is positive, slope is negative. If you're looking at the original graph, downhill is when the derivative is negative. Uphill is when the derivative is positive. So in general, the quick things we look at first are the places where, if you're looking at an original graph, where's the peak? And when you're looking at the derivative, when is it 0? Those are the first places we look. Okay, how fast is balloon A moving when balloon B is at its highest spot? So first you had to find when is balloon B at its highest spot. 8 seconds, that's right there. And then the question said, now I want you to think about balloon A. Now, are we talking about the height of balloon A? No, because the question is not saying what's the height of balloon A. It's saying how fast is it moving. So in other words, it's asking for this slope right there. But that's contained in the derivative. So we just need that derivative value right there. That's where the 2 came from. The slope of that black line is 2. Okay? And then we got a business example. Let's take a look at that. So here we go. Revenue and cost. They actually only make sense for greater than or equal to 0. So let's add that stipulation. X greater than or equal to 0. There we go. So there's our 2 formulas. And then we would talk in Math 111 about how the cost starts above the revenue because you haven't made any money yet. And usually there's an initial cost or a fixed cost. Anyways, and then as you move to the right, we can measure the profit. So let's take a look at the profit is the gap between them. I was going to graph that, so let's do that. We're going to do C of A plus TR of A. You don't need to know what I'm doing here. I'm just trying to quickly draw a reference for us. Here, go. So that's that gap there. Oop, too fast. So that's this. That's the profit. Oh, I don't want it to a negative. 0 to 4. Forward. Go. So there it is. That's the profit. It's biggest somewhere in the middle there. When it hits there, it's 0. All right. So the moment that the slopes are equal, when marginal revenue equals marginal cost, see if I can do this on the fly too, X minus A plus C of A, that's when they're furthest apart. And we've talked about this in a few different ways, but the moment when these 2 slopes are parallel right there is the place where they're furthest apart, which corresponds to maximum profit. Okay, so what was the question asking? The question first asked about average cost. So let's throw that into the mix. Average cost looks like this. The lowest point on average cost is actually an important point in practice, because if you ever get a selling price that's below your lowest average cost, you can never make money. It's called your break-even price. So there's a significance to that point down there, and you found that in one of your homework questions. If I'm asking for the marginal cost at 200, then you would say, well, here's total revenue. I would like to go to 200, which is 2 in this graph. That confused a few people. Let's go back here to 2. And I would like to know that slope, because the slope of that line will tell me if I go over 1, how much I go up. Okay, that's all that was asking. That's what marginal revenue is. Okay, give the longest interval when this is increasing. Well, it stops increasing when it gets to the top, wherever that might be. So it stops increasing when it gets to the top. So it sure would be nice to draw its derivative, which we can. We call it marginal revenue. And then we have the same thought process of marginal revenue is positive, which means uphill, and then negative, which means downhill. So the place where the marginal revenue is 0 is when your total revenue is highest. So it's going to be uphill from 0 to 5. Okay, what about profit? If we actually graph profit, it's weird to graph them together. I never do that because it looks weird. But that little gap that I was showing you, the height of that gap is the same as the height of the profit. So let's get rid of these so you can see it for a second. So however tall that is, so it gets really short over here. But the highest profit is somewhere in there. Get rid of that line. Okay, so if you can turn it into just a 1 function instead of 2, then you can just take the derivative and set it equal to 0. But you can also do it another way, which was that matching slopes idea, that the place where you're highest is the same place where MR equals MC. Okay, so there's some visuals. Hope that might be of interest to what you're doing. Everything we're doing here is not just pushing symbols. There's a physical, graphical significance, and that's what I'm trying to do here, is show you we're finding some pretty interesting things. And the point of this is it doesn't even matter what the function is. I could have changed those numbers, and the principles are still at play. That's why calculus has this really extreme reach, because it can handle any function. All right, hope that's interesting.